Hey guys, Ms. Marusik here, and in this video we're going to talk about calculating with entropy. Now in our previous video we looked at the idea that entropy is tied to the number of microstates, the possible arrangements of particles or energy within a particular substance. And we made some qualitative determinations on whether or not entropy increased or decreased throughout a particular process. And the way that we did that was by looking at things like the number of particles on the reactant and product side, or by looking at the state changes between the reactant and product side. The problem is that it's not always all that easy to make a qualitative determination on whether or not entropy increased or decreased. Sometimes we actually have to do a calculation involving what are called standard molar entropy values. And so that's what you see in this chart right here. We have some entropy values for both singular elements as well as for compounds. And I'm going to point out a couple of things about this data before we actually calculate with it. First off, you notice that none of this data has a zero value for the entropy. Let's talk about why. It says here that the third law of thermodynamics states that the entropy of a perfect crystal, meaning a solid that's in the perfect arrangement of those particles, at 0 Kelvin, meaning absolute zero, is 0. And you're like, okay. What that means is that at absolute zero, where there's no motion taking place, that there's really only one possible arrangement for those substances, particles, and so therefore the entropy value would be 0. But as soon as that temperature gets anywhere above absolute zero, now you're going to start to see some motion in play. And you're going to start to get a range of energy values occurring within that substance. And so that would mean for anything above absolute zero, you are going to have a non-zero value for that entropy. So for example, here, this chart is at 298 Kelvin. So being above absolute zero, none of these entropy values will be 0. So again, at standard ambient temperature and pressure conditions, which is where we do most of our thermodynamic calculations, all substances will have a non-zero value for their entropy because, again, there's going to be some movement and randomness to the system. Now, this is very different than what we saw back in Unit 6 for heats of formation. Remember, heat of formation is the heat associated with forming a substance from its original elements all in their standard state. But if I'm forming an element in their standard state, there's not a heat change associated with that. They're just present at those conditions. And so therefore elements would have a heat of formation of 0, but we don't see that for entropy. So just be very careful. Heats of formation can be 0, but entropy values are not going to be 0 for our purposes. One other thing I want to point out on this chart is that you'll notice that we see a particular unit being used for entropy of joules per Kelvin times mole. And sometimes you'll see them use the Kelvin to the negative first and the molarity to the negative first instead of dividing by those. So don't get panicked if you see it shown one way or the other. It means exactly the same thing. But what I want to point out about the unit is that we see joules being used in there. And the reason why we have to be cautious on joules is because a lot of our other thermodynamic data that we deal with, for example, enthalpy, is typically in kilojoules. And so if we're ever doing a calculation where we have both enthalpy and entropy involved, we have to convert one or the other in order to make those units match. So we just have to be really, really careful with our units here. Now, before we go any further, I actually want to pull up here for just a moment our formula chart to the thermodynamics section. Now, back in Unit 6, we looked at the MC delta T equation to calculate heat. And we also looked at this delta H equation where we saw the sum of the heats of formation of all the products minus the sum of the heats of formation of all the reactants. And we saw 3 equations here that all looked kind of similar, even though we only used one of them. Here's where we're going to start to use those other equations. So you notice here our entropy calculation is the sum of the entropy of all of the products minus the sum of the entropy of all the reactants. However, those entropy values for our substances are per mole of just that substance. But if what I'm trying to calculate is the entropy of the overall reaction, then I may need to take into consideration how many moles of that substance are in the reaction, meaning I'm going to have to take into account the coefficients. And we did see that when we used the heat of formation equation as well. All of our individual heats of formation had to be multiplied by their coefficient. So we're going to see that same thing here. Now, entropy is kind of interesting because this calculation alone cannot determine whether or not a process is spontaneous. Let me explain why. We have the second law of thermodynamics, which states that in any spontaneous process, there is always an increase in the entropy of the universe. Basically, the universe is designed to get more messy as time proceeds. I'll give you an example. Think about your room for a moment at home. More than likely, you would have to put in some effort in order to keep your room neat and tidy. If you just let your room go, it's going to get messier as time goes on. The number of microstates and arrangements for all of the stuff that's in your room is going to increase. And the universe works exactly the same way. The universe is designed to get more messy, meaning if the entropy of the universe is positive, then the reaction is thermodynamically favorable. It's spontaneous. But here's the problem. This equation up here doesn't calculate entropy of the universe. It calculates the entropy of the system. And so it doesn't take into consideration what's going on with the surroundings. And so I can't use just this equation to determine spontaneity. We're going to have to use an additional equation that we'll talk about in our next video. However, with that said, let's go ahead and talk about how I would use this equation as is. And so they give us a reaction down here on our example, and it wants us to use the values of delta S in the table above to calculate the entropy change of the reaction. So I went ahead and rewrote the equation that I saw up here. And once I see I'm doing a products minus reactants scenario, I do go ahead and label my reactant and product side up here. I can't tell you the number of times I've seen people get those two mixed up and then they mess up their calculation. So then I say, okay, well, on the products, I have water vapor. And so I go up here to my table and I go find water vapor, which has an entropy value of 188.84. However, that is per only 1 mole of water vapor, and I have 2 moles of water vapor in this equation. And so I need to multiply that value by 2. Now that was our only product, so then I want to subtract the sum of the reactants. Now you notice I did put those reactants kind of together in their own parentheses. That is to maintain that order of operations. So just be really careful with that. Our first reactant was H2. So I went and found its value above in the table and I multiplied by that by 2. So that gives us 2 times 130.7. I then went and found the value for O2. There's only 1 mole of that, so I did 1 times the 205.1 from the table. Now, I didn't put units when I wrote out my equation, but I want to talk about units for a second. Again, the whole reason why we have to multiply by the coefficient is because the value that you're getting from the table is joules over Kelvin times mole of the substance. But I don't want moles of the substance for my overall value. I want moles of the reaction. So by multiplying by the coefficient, that coefficient is telling us the moles of the substance per mole of the reaction. And you can see here what that would do is it would get moles of the substance to cancel out, leaving us with that unit of moles of the reaction. Once I take all that math and plug it in my calculator, that gets a delta S value of negative 88.82 joules over Kelvin times mole of the reaction. And so I want to ask myself, well, does this negative make sense for the change in entropy? A negative value would indicate a decrease in the entropy. So let's look at this reaction here. Let's see if a decrease in entropy makes sense. Now, the first thing I would always want to check are states, because states are almost more important than the coefficients are. But I notice here that everything is maintaining as a gas throughout. Now, if I saw a gas on one side and not on the other, then that would be a really key factor on determining entropy change. But here it's the same all the way through. So I need to utilize the coefficients. I notice here I have 3 molecules of reactants, but only 2 molecules of products. So the entropy makes sense because the reaction has a decreasing number of moles, which would cause a decreasing amount of arrangements or microstates, which would support a decrease in entropy. However, I'm going to tell you something about this reaction here. I know we see a decrease in entropy, but what if I told you that this reaction is spontaneous? It is thermodynamically favorable. If I have hydrogen gas and oxygen gas, they will naturally react to make water without a lot of outside intervention. And the reason why is because I'm not taking into account here what's going on with the surroundings. This is only the entropy change of the system. So even though I want entropy to increase, there must be a huge increase that's occurring in the surroundings because I have a decrease happening in the system, even though I know this is thermodynamically favorable. So again, you have to be careful here because I can't use just what's going on with the system in order to determine thermodynamic favorability. I really need a little bit more information. And so that's what we'll see in our next video. All right, I hope you're feeling good about calculating with entropy. We're going to be doing a little bit more with it in our next video. If you have any questions or need any help, please feel free to email me. Bye, guys.